As soon as it connects, I will start talking. Okay, we are now live. Welcome everyone. This is day 2 of the virtual summer school, OpenGeoHub Summer School 2021. We are very happy to have, with the yesterday days, we're very happy with the discussion. And we're very happy that we had a lot of questions, a lot of interesting discussion. But before we start, some of you are connecting now for the first time. I would just like to tell you about the summer school and something about the basic rules, what we do and what we don't do. So just very quickly, the summer school is virtual. It's also streamed live on YouTube. And we are super happy to have so many lecturers. Every day there are 5 lecturers and very diverse topics. And I think we cover lots of fields in spatial statistics and spatial data science. We are really grateful for all the lecturers for joining, and of course we are grateful for IFGI, University of Geoinformatics, University of Munster, Institute of Geoinformatics, University of Munster, for helping us organize this. We are going to have today 5 talks. They're split in 2 blocks. The blocks you have to, in the second block, you have to reconnect, and then you can follow the second block. We have also some little social event. And in the social event, you can split into smaller groups and spend talking. The social events are not video recorded, broadcast. The main talks are recorded and broadcast. We got a lot of registrations. We see that some people did not manage to connect, but yesterday it was all about, I think, up to 200 people on Zoom at one moment. So there's really high interest. And also we are happy that registrations are more or less spread equally for each lecturers. And there is the hackathon also. If you're applying for hackathon, then just have in mind that we usually declare winners the next day or the day after. And the winners are declared by the corresponding lecturers. This is the social activity. So we go to this Wonder Me, and then you can move to a group and you can spend time chatting. Anything else I would like to say? We are planning for the Summer School 2022. So keep your radars on, subscribe to our Twitter and YouTube channel. And most likely it will be hosted by 52 North in Germany. We're just still looking at the details because of the coronavirus. Of course, everything's complicated, but most likely it's going to be a physical event. So also with the live broadcast. And with this thing, I stop sharing and I pass on to today's chair of the first block, Professor Eze Pebesma from IFGI.
Thank you, Tom. It's my pleasure to announce the first speaker of the first block today. That is Eje Rubak. Eje is Associate Professor at the Department of Mathematical Sciences of Aalborg University in Denmark and specializes in the analysis of point pattern analysis. He's one of the authors of the famous book, The Spatial Point Patterns, Methodology and Applications with R, which is really the Spatstat Bible, so to speak. At least that's how I call it. And the topic he will talk about today is analyzing spatial point patterns with Spatstat. Go ahead, Eje.
Okay, thank you very much, Etsa, and thanks to Tom and OpenGeoHub Foundation. It's really a pleasure to be here. And I will share my screen. First, I'll start out with a few slides, and then I'll go more to a tutorial. And just in case you haven't seen it yet, here's the web page. Maybe I should use this so you see spatstat.org/OpenGeoHub, so OGH 2021. And this is where you can find there was some preparation material and the slides and the tutorial here. And there's a GitHub repository containing the sources for everything. When we talk about spatial point patterns, the biggest package on CRAN is Spatstat, and that's where I'll focus my attention here. And so this session is really just very short introduction with these slides. I have 11 slides, and then a live tutorial with examples of analysis, and then we'll have some time for questions and discussion. And the Spatstat package is quite large. It's 25 years of development, mainly by Adrian Baddeley in Perth. And in the beginning, he was joined by Rolf Turner. And then more recently, I've joined also the team, the Spatstat team. And over the years, it's grown too big, really 100,000 lines of R code and lots of C code and many, many exported functions and objects. And at some point, Kran told us that this is just too much for a single package. And we agree, it was just a pain to start splitting up something that was already packaged in one big thing. But we're through that process now. So really, when I say Spatstat, it's really more of a suite of packages, all called Spatstat.something. We still have a package called Spatstat, but it's mainly empty with some documentation and vignettes, and then it depends on these other packages. So if you type library Spatstat, you really get everything loaded, and that's what we'll use here. And Spatstat has a design where there's been a strong focus all the time on backwards compatibility. So we don't break things all the time, so we're not as fast developing and using new concepts as other packages. It's very much following the base R design and uses base R graphics. Of course, you can take the calculated objects and then plot them with ggplot, etc. I do that myself every once in a while also, but the basic for exploration and the default things happening in the package is just base R graphics. And it's really centered around the S3 object system, and it has its own objects for data, etc. This is historical thing, and it's not going to change soon. Luckily, people developing new infrastructure packages have been very kind at developing conversion tools also. So you can easily go between SF objects and Spatstat objects, etc. And we've done quite a lot of work on the documentation. So you will see that most functions have really extensive documentation, also explaining some of the mathematics underlying the functions that we use. And then I always try to promote new users really to look at just the package help, just question mark Spatstat. It really gives like an overview of a lot of functions and functionality. So take a look there if you need some specific thing, go through the sections and see there like lists of functions. So what do you use Spatstat for? Well, you can use it to just as a basically descriptive statistics kind of thing, where you do calculations, and it's fairly efficient with this calculation. We can handle reasonably large point sets, like hundreds of thousands is okay for many things. Other things, more complicated models, etc., is not going to work if you have a huge data set. So it's like calculating pairwise distances and summarizing what do these points, how do they look like. Well, that's of course one thing to use Spatstat for, but really the focus is actually on statistical inference, and where you really think about that this should be locations, this point pattern should be something that's generated at random by some process, and you want to make statistical inference about the process. So we think about point processes. So it depends really on your questions of interest, whether you should treat it as a point pattern or not. If you really think the locations are just fixed, there are drilling sites at some points where you have different measurements and you're really interested in the values at these drilling sites, well, then you're not really interested in the random mechanism generating the points. You're interested in the values, and probably you want to go into geostatistics and stuff that Etzer does really well in his packages and other people. So so that's really the main thing, should be that you really care about the random locations of your process. What does random locations look like? Well, if they're completely spatially random CSR, they're just a Poisson process. So there's a Poisson number of points and they're completely independent of each other. And here are 3 realizations just to show that, well, this is what randomness looks like in terms of spatial points. On the other end of the scale, we can have very hard interaction in terms of inhibition between points. This is what Gibbs processes are very good for. Here's an example of a hardcore process where you can see that the points can really not get too close to each other. That's another, but still there's a random mechanism generating these random point patterns, and we want to make inference about that random mechanism. And in the other end, we have the cluster process where things tend to cluster. In this case, it's a Thomas process. So what happens is that on average, it generates 5 cluster centers at random points. And then for each of those, a Poisson number with a mean of 20 offspring is generated within with a scale of 0.1 means that these offspring are distributed with a bivariate Gaussian bell shape with this standard deviation. So that's really the core concepts that you need to have in mind when we start doing modeling with Spatstat. And then finally, there's another type of Poisson process called the inhomogeneous Poisson process. And in this case, the points are still independent of each other, but they're not homogeneously spread across space. This function in the x and y coordinates really prefers bigger values of x and y. So when both x and y are bigger, we tend to have more points and less points in where we have a very low intensity in the lower left-hand corner. And there's a fundamental issue about this thing about, do you have an inhomogeneous Poisson process, or do you have a Thomas, sorry for the spelling mistake in the top, a Thomas cluster process, for instance. Here we also see that it looks like there's a tendency for points to be in certain areas and other areas are empty. So this is really something that's hard to distinguish, whether you have real clustering where the points attract each other, the fact that there's one point tends to attract a new point, or if you just have that underlying, this is a favorable area to be in. And here we can kind of see, well, because we have replications, we can kind of see, well, it looks pretty random where these clusters of things are, they move around. Whereas when we look at the inhomogeneous Poisson process, it's always in the top right-hand corner, we have most points, and in the lower left-hand corner, we have few points. So here it is really an intensity thing, and in the other one, it's clustering. But we would not be able to see this when we just look at a single realization. So that's something to be aware of, that it's a fundamental problem, whether you are looking at something that's really related to the intensity and the general abundance of points, maybe due to there's more favorable conditions for plants to grow in this area, whatever, or whether you're looking at interactions that one point tends to give rise to a new point, maybe in terms of offspring, etc. And often what we actually do to analyze things is very analogous to what you do in time series. Either you can assume stationarity, and then you know that what I see in my data is a glimpse of something that in theory extends for infinity, and it has the same statistical properties. So if I calculate statistical properties in my little glimpse of things, it is something that tells me something about the entire process. Or you can do this two-step thing where you say, well, first that I can see there's some inhomogeneity, or I choose to model it as inhomogeneity, and I model the trend, the mean of the intensity, as you do in time series, find trend, seasonality, and after accounting for this, you can model interaction. That's really the standard approach. And then as a final thing before we go to the tutorial, just very quickly, again, use the Spatstat help, the general package help, to find specific functionality you're looking for. If you need to learn even more, you can get the book Edsa mentioned. It is really quite a big book, so I'm not going to go through all the pages today, but of course I'm going to tell you some of the things that are in there. And unfortunately, we were not on the wave of being able to do free online versions of books. We hope to do that with a second edition. And then You can find more details about the book at this link. And otherwise, ask questions on Stack Overflow. There's quite a few people using the Spatstat tag, so you can also find solutions to your problems there maybe. And we use GitHub for feature requests and bug reports, etc. Okay, and with that, I want to go to the tutorial. And in this tutorial, as I already mentioned, it's also in a rendered version online. And I suggest if you're following along, maybe you should actually have that open on an extra screen, or mainly focus on that if you can. I have a limited real estate here, so sometimes I have to jump a little bit between plots and output. So of course you need Spatstat installed, and this tutorial is very terse in terms of comments, etc. So it's really the intention that you follow along and see this video. You cannot just read the tutorial. It's not a vignette that goes through all the details. An easy way to get the development version by now is to use this RUniverse thing, which is very nice for package developers. So this is an easy way to make sure you have the newest version of Spatstat. For this tutorial, the CRAN version is just fine. So now I see that I didn't clear my R session. If I'm lucky, I can just restart R here, just to get everything from the start. When I type library Spatstat, you will see here in the apparently it didn't. Yeah, now the output is coming here. That really this loads a bunch of packages. So this is what I talked about, that we split Spatstat into parts. A very important point when you start doing practical things and use your own data is that basically everywhere in Spatstat we assume we have planar coordinates. This means that they've been projected to a flat space, and that's assumed. So if you just give latitude, longitude points and call them X and Y and start analyzing your points, you can do that. And in many cases, you can make some sense of it, especially if you do some appropriate ratio between the latitude and longitude. But in general, this is a very bad idea, and you should make sure your points are projected. Go through SF. It has all the nice tools. If you're in doubt about projections, I find myself using this projectionwizard.org to help find a good projection for the area at hand. Sometimes you can find SP and map tools can be used for some specific classes of Spatstat things that are not supported by SF yet, but it'll be rare. So, and to save time, I'm not going through the process of reading in new data, etc. You can use the methods in SF. So I assume most people will go through, read data into SF, and then use as.ppp or some other method for the Spatstat classes. So we'll just look at the built-in, one built-in data set here. And this is called Chorley, and it's cancer cases from the Chorley-Ribble or Chorley and South Ribble Health Authority, where we have two different cases of cancer, where we have the home locations. And in this case, we think of this as a random pattern. The fact that there was a patient in this specific location that had that was diagnosed with lung cancer, it might as well have happened in any other spatial location in this area where people live. So this is a point pattern, and in Spatstat terms, it's called a planar point pattern, a PPP. And if we look at, so the class here is PPP, and a way to find a lot of Spatstat functions also that I also turn back to every once in a while is to remind yourself what kind of methods are available for this class. And in this case, for PPP, this planar point pattern, it's probably the most supported thing in Spatstat. It has 108 different methods. So there are a bunch of different things where you can find kernel density estimation, ROC curves, area under the curve, and whatnot. So this is a way to see, well, we really use this S3 methods. And if we do a summary of the data set, it gets like quite long here. One of the main points I wanted to go through was that you see there's a summary of the polygonal boundary enclosing this area. And this is because the boundary is part of the object. A PPP contains the points and the boundary. And sometimes this is annoying when you have your data, you just have a bunch of points and you have no idea what the sampling region was. Well, how should you then make the region? Well, it's a conscious design decision in Spatstat to say you need to supply a region. For even the simplest things, as we have here, where we say, what is the intensity of larynx cancer patients? Well, it's 0.18 cases per square kilometer. That would, of course, be a different number if you embedded this in another region. If you made a smaller region or a bigger region, you'd get another number. So to just talk about the very basic things of point patterns, you really need to have an enclosing region. Of course, if you use Spatstat just for descriptive statistics where you don't really make any inference and you just need like the machinery of calculations, you can just define the bounding box of your points or whatever, and everything will work. And this is what's done by default if you import data that doesn't have any information about the window. Okay. And windows are supported. You can do calculations with them. So the window of the Chorley Ripple is it's called an O-win, and it's a polygon. You can do polygon operations with it. You can make the dilation or the erosion, and we can see what they look like here. So the original window here in the middle, erosion is the smaller one, dilation is the bigger one. This is all using the polyclip library. So the advantage of this, what we ended there, was that we wanted something that was independent of having really geo-computational libraries installed. So GDAL, all this stuff is amazing, but sometimes it's challenging to install it. It's become easier over the years, but so Spatstat is independent of these. This also means we don't support coordinate reference systems, as everything is in a local coordinate reference system. And you need to be able to handle that when you go back and forth to SF or whatever you do. So what I would like to talk about as a case study, which is easily understandable for everyone, I think, what is the objective, what are we doing? So I'm not going to do a complicated analysis from biology where we look at cells that have different interaction patterns, whatever. We look at gold deposits. So this is a nice older data set from the Murchison area in Australia. And Murchison is a built-in data set again, and that's really a list, a spatial object list, which has a point pattern, it has a line segment pattern, and it has a polygonal boundary, which shows where there's the outcrop of a greenstone, a specific type of rock. For when we start making models, etc., it'll be more convenient to have the units in kilometers. And again, Spatstat is not particularly clever about coordinate systems, units, etc. So you have to rescale it yourself. There's a function to rescale it, and you can give names to the rescale units. So here I call them kilometers, but Spatstat doesn't know there's a factor 1,000 between kilometers and meters. So again, this is pretty basic, and the design idea is that you have your local coordinates in the format that you like them, and then you do all your analysis there, and then you have to transform back if you need something where you have proper units, etc. So we have now 3 different objects here. We have many different objects because I didn't apparently clear my thing before. But we have the point pattern of gold, the fault lines, and the greenstone. And there's a function called distmap, which uses a FFT to fast calculate the distance to any geometrical object. So it could be to lines or to polygons or whatever. So this dist map is simply a raster. Now it's called defaults, and this EPS argument says that we want a 1 kilometer resolution. So this defaults is what's called an image, and it's a 400 by 300 pixel array, and that's because the region of Murchison is about 400 by 330 kilometers size. And we can plot the resulting dist map. So it's an image, which is the raster format in Spatstat. And we can see that it's the fault lines are hidden in here in where there's a 0 distance, and then we get the distance to everything. We can add, and again, base graphics. So it's simple, it works, but you cannot do as fancy things as you can in ggplot. So here I've added the fault lines and the gold deposits. So basically all the plotting commands allow you to do add equals true to put it on top of something else. So if we think about, I mean, looking at this picture, you don't need to do statistics to say, well, gold tends to appear closer to the fault lines. So the idea is that fault lines, you can observe them more easily, and then you can know, well, is there really a connection between fault lines and gold deposits? Then you can say, I want to explore more intensively around the fault lines and ignore areas far away from fault lines. And there's a function to divide space into a division of space is called a tessellation. And if you want a tessellation according to specific quantiles of something, we can use this quantess. So we use a tessellation of the window of gold or any of the windows, the Murchison window. And then we say we take quantiles in terms of the false image. And now I've chosen 4 quantiles, so I get the quartiles. And that's fast. And if we plot it, we see here that the 1/4 of the area is blue and 1/4 is purple, orange, and yellow. And of course, that's a very simple way to check, does the gold tend to be around the fault lines? You can just count with quadrat count, how many gold deposits do we find in each subdivision of space. So quadrat counting is usually used for square subdivisions of space, but you can equally well do it with some other arbitrary subdivision of space with using a tessellation. So if I count the gold in these 4 areas, and I can make a bar plot, we can see that we have in the close vicinity, we have 230 gold deposits, 25 in the next level, and 0 in the rest. And of course, if we see we do this in a finer resolution, we clearly see that they really tend to be close to the fault lines. And there's a more developed statistical theory where you actually look at if there is some relationship between the intensity of gold and this one covariate, the distance to fault lines, what could it look like? And that's a kernel smoothing technique where we can get confidence, like point-wise confidence bands for this estimate. Sometimes with these zoom things, the automatic legends in these base graphics go crazy. It looks nice when you put it in a figure or a PDF or whatever. So this is supposed to be a small legend box up here. You can use, you can get predictions from this. So there's a predict method. So again, the row hat, when we estimate this smooth relationship between gold and distance to false, there's a predict method. So you can look at what is the predictions of gold deposits in this case. We can compare this with what if you just do normal kernel density smoothed estimation or adaptive density smoothing, where you're using variable bandwidths to that's the main problem about kernel density estimation, is to find a good bandwidth, and is the same one good for the entire survey area, is just to show that we can do it in Spatstat. And I've wrapped everything as a spatial object list. This means that you can keep it together and plot it together. So we calculate the kernel density estimates, etc. And when we then plot the object, we see, and there's not a huge difference between the adaptive one and the kernel density. But the predictions, according to a model where you believe this row hat relationship to be true, it looks very different. It really says, well, gold occurs close to the fault lines, and that's it, nowhere else. So that's this is kind of exploratory things where you can look at these relationships. We also have an implementation of the ROC curve. So if we imagine looking at, well, what are the distances actually where we find the gold? So we have this 255 gold deposits, and we can record at what distance to the fault did they appear. So we use the subsetting here just to subset with any spatial, like it could be a subset of the polygonal region or specific spatial points. That's what we do here. Say we want this raster at these spatial points. So this M at this PPP. We can figure out, see what they are. The problem here is, of course, that this dist map is a discrete approximation, and I chose the epsilon to say what resolution do we use. So actually, there's also a method or a function called distfun, which really returns a function. So you can evaluate from this point, like a function of x and y, from this point x, y, how far is it to the fault lines. So this distance function, it says it measures the distance to any of these 3,252 line segments. And if you use that function on a PPP on spatial locations, it just evaluates at the exact XY coordinates. And this is actually somewhat different than using the discrete approximation. Of course, it's in the same ballpark, but it can be quite different to use such an approximation. And one simple thing to do would be to say, well, what if I made uniform random points that look like the gold deposits? So this example pattern of golds means that I make uniform points according to this example. So with the same, in the same spatial region, with the same number of points, they're just uniformly spread, generated. And then you can look at what do the fault distances look like for them. And to no big surprise, the uniform points here in the background appear at all kinds of spatial distances, and the gold only appears at short distances. And this is really what the ROC curve is doing. It's comparing the distribution of these distance to the fault lines for the gold deposits compared to randomly selected points. If we look at the ROC curve here, we can see the interpretation is, if I use this distance to the fault lines as my covariate, then when I have, for instance, 10% of the covariates that give me the 10% that are closest to the fault lines with the lowest value of the covariate, then I actually have 60% of the observed gold deposit. At 20%, it's more like 80%, etc. So there's a clear interpretation of the ROC curve, and you can use it in terms of what is the power of this explanatory or this predictor. How well does it predict the occurrence of gold? And then really, this is kind of exploratory and to figure out other relationships, etc. And then what really Spatstat was developed for was to fit statistical models. And I know it may sound a little bit old school to some of you in these days, but there is still value to having a parametric model where you have clearly stated what are my assumptions, and you can critique the model and say, well, this part is not fitting correctly. Maybe I need to take this into account, etc. It does really, this traditional statistical approach provide some valuable insights. So this is really in the spirit of LM, GLM in R. So what you do to fit a model is to use PPM, so point process model, instead of a linear model or generalized linear model. And then you say your response is the gold pattern, and your explanatory variables are given as a formula as you're used to if you do regression in R. And the EPS here is because when you fit a model to calculate the likelihood and maximize it, there's really a spatial integral going on. And of course, you cannot in practice calculate the precise spatial integral. So it's discretized, and it's discretized in a clever way so that everything actually turns into a GLM, a weighted Poisson regression. And then GLM is called under the hood, and the results are collected and interpreted in terms of point patterns. So that's really the main purpose of Spatstat when it was developed, was to help people fit these types of models. Depending on how small an epsilon you set, the longer it will take. This does give a pretty fine discretization of this integral. And as you see, the output of such a model is something that you'll find similar to LM. So there are some fitted trend coefficients. And this is extremely important that this is on the log scale. It says here it's the log intensity that depends linear on the distance to the faults. So there's an intercept term and there's a negative slope. The further you go away from the faults, the lower the intensity. On the log scale, it's linear. So it means that in practice, it's decaying by a factor of e to this thing. I think I have it a little bit further down in the notes. But it's really important that we are doing things on log scale, and sometimes people misinterpret this. It's just like a GLM with a log link. So the fitted model here is in terms of that the intensity is a log linear model. And I guess this looks nicer in the rendered output. So if I just run this down, down here. So actually, for every kilometer you go away from. This is the baseline intensity. So you find 0.01 gold deposits in the near vicinity of the fault lines when the distance is 0, and for every kilometer you go away from the fault lines, it decreases by 75%. So you can really see the effect of this distance to the fault lines. And then you have an object, this model object, the fitted model, and you can do all kinds of evaluation of your model. So an effect function is just really to show you what is your effect of this covariate. So this is just showing us that we've really fitted a log linear, so an exponentially decreasing intensity here, saying, well, the intensity of points close to the fault lines is this, and as you go away, it decreases exponentially. And these objects, the result is an object of class PPM, just like an LM object, and it has a bunch of different methods, etc. You can also simulate the model. So here I simulate 8 realizations of the model, and then I add to the list a 9th pattern, which is the gold pattern that we had in the beginning. And here you can probably clearly see that we don't have a perfect model at this point. Like, these are random realizations from the model, and this is the gold pattern. So it's clear that if anybody asked you to point at the one that sticks out, you would say, well, this one is kind of different. The points are closer clustered together. You can fit models with 2 covariates. I think I won't go into the details here due to the lack of time. But basically, you fit a model in the LM spirit, where you can either have an additive effect or an interaction effect. So here, this greenstone was a polygonal region. So we have these areas where there's greenstone, and if you use that as a variable in Spatstat, it thinks of it as a factor variable. So it says either you're inside the greenstone or you're not inside the greenstone. So it's going to be converted into true false, and then you're going to have a shifted relationship whether you're in the greenstone or not. And you can do all the traditional things that you can do for GLMs, not all of them, but many of these things. So you can do a formal test between nested models as here and using ANOVA. So a lot of this is really the evolution of Spatstat, is to develop the mathematical theory underlying this and then to implement it in Spatstat. And if we look at the interaction model where we have two different log linear models, one inside the greenstone and one outside the greenstone, you get a slightly better fit, but you'll still see that there's something a little bit different by this pattern. But by now you have accounted for making patterns that look somewhat like your observed pattern. Then we have model diagnostics. So really do what you would usually do when you criticize a generalized linear model. Look at leverage, influence, DF betas is like how much is the each of the parameter estimates affected by the data points. Leverage is an interesting thing here in the spatial stat, because it's really something that's tied to the spatial area, right? Saying this specific spatial area with its configuration of covariates, of explanatory variables or predictors, how much does it influence the fitted model if I have a point or if I don't have a point here in this spatial area? So if we look at the leverage here, you see there are some points that are really sticking out here. And if we add the fault lines and the outline of the greenstone, you'll see that where we have really high leverage in this case is where we are inside the greenstone area, but we're far away from a fault line. The nearest fault line is somewhere out here. And it's the same kind of thing here, that we have a region of space that's far from the fault lines, but it's inside the greenstone. And the model, that would really affect the model a lot if we observe or don't observe points in such a region. So it's nice to understand what's really driving things when you're using these covariates in this setup with this leverage. And the influence is about the actual data points. And you can see there's a huge influence up here and an influential data point here. There's also one here. And this is, again, a point that's inside a greenstone area, but far away from the fault lines. And if you had more times for looking at the details, you can use the DF betas to figure out how, with these influential data points, how do they affect each of the covariates? How do they affect the greenstone parameter or the distance to the fault lines parameter? So this is really the main message here, is that I really want you, if you're a researcher in some field where you do point pattern analysis, start out fitting parametric Poisson models to your data and criticize them and look at what can you get from this. It is a powerful tool to understand your data, and your assumptions are very explicit. So you can always criticize and say, well, this parametric model is unrealistic, it's not log linear, etc. But you clearly say, what are my assumptions and which ones are not fulfilled, and how could I improve? And then, of course, Poisson models are in many cases too simple. I would actually say if you have enough information, enough covariates, predictors, a lot of times you get really far with Poisson models. But the problem is that there may be underlying spatial things that you don't have observed where you don't have the information. And log Gaussian Cox processes are quite popular models for clustering, and they're supported in Spatstat also. And then it's called KPPM, the command to make a cluster point process model. And again, you specify the mean in the same way as you would in the GLM or in the PPM case. But now you add an extra argument saying, well, what type of clusters do I think of? Is this a Thomas process where we have Gaussian clusters, or in this case, a log Gaussian Cox process where the clusters are generated by an underlying log Gaussian random field? And fit the model here, and it's also relatively fast. And if we look at the coefficient summary, that's really a clue here to say, well, if we have clustering, we're really too optimistic when we fit the Poisson case, because then we are saying, well, all the points are independent, so they all provide equal amounts of information about the relation between the response and the covariate. But actually, if there's clustering, having several points is not as much evidence, because they can just be appearing due to clustering of points and not due to the underlying intensity. So what really happens is that when you look at your standard errors, they are inflated by using a cluster model, and they may be more realistic if you really have clusters in your data. We can compare here in this case that all the standard errors are smaller in the Poisson case compared to the cluster case. And it may look slightly better here when you look at the simulations, that you tend to get some more clustering, that you think this may look more realistic in terms of the actual gold deposits. I know this is very informal model diagnosis, etc., but I actually like it just to see, when I formulated this very specific parametric model, what kinds of output does it really provide me? Does it at all look realistic? So I think it's a good extra visual tool to throw around. And then in the other case, as already mentioned, we have Gibbs models. I already showed you a Gibbs hardcore model. Here I've taken a Strauss hardcore model, where basically you say, well, points are not allowed to be within some given distance of each other. They are 100% repelling each other within the hardcore distance. And that's, in this case, now I'm simulating data. I say in the unit square, since I don't provide a window, and I say it's 0.03, they cannot come closer than that. And in the next part up to 0.06, they're allowed to interact with each other. So here of course, they're also interacting. In the other case, they're completely repelling each other. In this case, they tend to not like to be within this range. And we have this gamma parameter, which is a number between 0 and 1. If it's 1, they're independent of each other. If it's 0, it's hardcore. They cannot be close to each other. And if we look at such a model, that again generates these kind of inhibitory looking point patterns. And Spatstat has a lot of well-developed tools for Gibbs point processes also. So you can explore that more on your own hand. Again, you can do model fitting. It uses what's called the pseudo likelihood, but you get like a fitted model with coefficients, estimates, etc. And another tool, which is almost the first time I've tried to suppress this through an entire point pattern analysis lecture, is the Ripley's K function. So this is a summary statistic where you try to summarize the pattern and say something about how does this look like compared to complete spatial randomness, for instance. And it has a nice interpretation in terms of the expected number of points in a normalized fashion that you that you see around a given point of the point pattern at different radii. And this nice smooth curve pi r squared is what you would expect if it was a homogeneous Poisson process. And we clearly see that at these distances, we have fewer points than expected in the random case, and then it picks up again, and we get close to the Poisson case. So it's a kind of diagnostic tool or understanding whether you have clustering or not. But again, it's very important that you need to consider that it could equally well be a case where you have inhomogeneous point pattern that is not really interaction, but it's some trend that's affecting the distribution of points. And there's also the pair correlation function, which is recommended in many settings since it's a more local thing that is really telling you that at these distances we see no points close together. Then we see more of them in this range, and then it starts being independent of each other in this range. Actually, we see more points than expected here in the beginning. And then I guess a little bit depending on the amount of questions, I can mention a few other things, or we can jump to some questions at this point.
Let me find my microphone. Yeah, let's first do some questions, and if we have time left, then you can jump back to more examples.
Yeah.
There were a few questions. Let me see. There is one in the Q&A session that I will now read aloud. You can also see it. Thank you for this talk. How many points can be dealt with in the fitting functions? And question 2, what is the best way to deal with an inhomogeneous intensity when using ppm, for example?
So, I mean, in ppm, you explicitly model the inhomogeneity. So you can specify covariates as we did in the example with the fault lines, where we say really the occurrence of points is depending on this covariate, the fault lines and other covariates that you can add in any fashion like. This also accepts other special things such as marks and x and y and functions of these. So you're allowed to use the x coordinate or the y coordinate as a predictor as well, or the marks if you have a multi-type where you might have different types of deposits. It could be either gold or silver, and you have a mark saying whether the deposit is one type or the other. You can also make a model that says, well, these are either completely independent models or they're proportional to each other, etc. So handling inhomogeneity in ppm is really about specifying the trend in the formula here. And the size of patterns that we handle is, so I've done something like 10,000. I've never done something like 100,000. It's doable, and I'm not sure that that's entirely true what I'm saying here. There is a method in ppm called logi. So here we use a type of logistic regression. It's another way to do the discretization and find the approximate maximum likelihood estimate. And it's unbiased no matter how small a discretization you use. For the maximum likelihood estimate with the standard approach, you really need to have a fine approximation. So you need many really dummy point locations where there didn't occur gold together with the gold locations. But when you do the logistic regressions, you can do equally many of each, or you can even do fewer dummy points. And it just takes this into account in the parameter estimates uncertainty. So if you have big data and you want a parametric model, I highly recommend that you use this logistic regression method.
Thanks. So then we continue with the questions on the Mattermost. The question from Tom: can some machine learning algorithms be combined with the Spatstat, for instance, for regression estimation? Are you aware of any examples?
No, so I think you can. What I've seen is typically people somehow transforming intensity images or point images or something, and making some kind of machine learning on covariates, and then kind of doing some transformation of the covariates or combination of the covariates according to these things, and using them in Spatstat afterwards. But we haven't had the time yet to really develop machine learning methods. So there are regularization methods. If you have a lot of covariates, you can do lasso type estimation to have shrinkage, etc. But proper machine learning methods, I haven't really seen that a lot.
Okay, thanks. So another question is, can we plot point processes and intensity plots over a real map, for instance, with map view or leaflet?
Yes, so the way I've done this, I've done this quite a bit, is to use the SF interface and transform back to an S. So if I have a real area where I have my covariates and points, etc., I have all that as SF objects. Then I take the points into Spatstat, and then and also you can transform the covariates and everything, and then you can also do the like the base plotting in Spatstat. If you plot first your covariates as an image and the point patterns on top, you can put everything in using the Spatstat stuff, but otherwise you have to go back through SF, and that's what I've done. I've sometimes made a small function that does the conversion on the fly, so I can do
maybe
like,
send the examples, so URL to examples, so to somewhere people can see. Just send it through Mattermost.
Yeah, I might actually expand on the tutorial and add this at the end as a nice example of. Because this is the brilliant thing about especially map view, map edit. I love these interactive tools for exploring, and we were just they arrived too late for really easy incorporation in Spatstat. We even have small interactive things in base R graphics in Spatstat. So if you have a plot of the gold pattern, and you want to look at a specific detail or something like that, you can define a box by clicking click box here, and then if I want to look at this top corner, I can click there, and now it's saved B as an object. I can plot the gold within that box. So I use the subsetting area, and I have that. And this was exactly because of this. You lack this interactivity when you're trying to understand details of a specific analysis. And we did this 5-7 years ago when MapView wasn't really well developed and all this stuff. So there are some of these kind of rough interactivity things in Spatstat, but clearly the MapView stuff is brilliant. I really like it.
I think for intensity plots, you would go for grids. You would go either through raster or through stars or through Terra or something like that. Another question. You mentioned the
1 minute to go.
Yeah, 1 minute. You mentioned the second edition of the book. When will it be available?
So we just talked to the publishers that they were interested in making a second edition. And with our speed of things, I think it'll be 2 years still.
Okay, yeah.
Yeah.
And then the last question. You made this example of randomly generated points, but would this approach also be relevant for diagnosing spatial autocorrelation? How does it differ, for instance, from Moran's eye?
So you're thinking about comparing. So you really have raster data, and then you sample points with different types of sampling mechanisms from Spatstat, and then you look at how do the covariates differ according to the sampling mechanism. I haven't really thought about that in any detail.
I think Moran's eye is more like for geostatistical processes, right? Correlation in attributes rather than
exactly. So
rather than patterns in points.
Yeah, so I'm not sure how this is related to these randomly generated points. I know Spatstat is used a lot to make some like regular sampling or clustered sampling of points. And we've also made this interface that you can actually use the ST sample in the SF package to call Spatstat functions for generating these kind of Thomas processes or whatever.
Yeah.
Okay.
Again,
Okay.
thanks a lot for the presentation. It's 2 o'clock, so we will continue with the second block. And the second block of this day will be given by Gerard Heuveling, a former colleague and good friend. Gerard is a professor in pedometrics and digital soil mapping at Wageningen University. He focuses on the development.
It's just a correction. It's not Gerard Heuveling. It's Judith and Oliver.
Oh, sorry, I'm no problem. I'm in the wrong. Sorry, I saw.
No problem.
Thank you. Okay, I'll start again. So it's my pleasure to give the floor to a former colleague, Judith Verstegen, and who will, together with Oliver Schmitz, present the second block. Judith Verstegen is assistant professor at the Laboratory of Geoinformation Science and Remote Sensing of Wageningen, the Netherlands. Her research interests are geosimulation models. Oliver Schmitz is a research software engineer at the Department of Physical Geography of Utrecht University, the Netherlands, and specializes in the developing GIS and geosimulation software. Their topic is geosimulation using fields and agents. So go ahead, Judith and Oliver.
Thank you, Edzer, for the kind introduction, and thanks a lot to OpenGeoHub for inviting us to give this session in the summer school. We are very honored. I will share my screen. So the idea of our session is that I will first present the concepts that we are working with in a presentation of about 15 to 20 minutes. And after that, Oliver will give a demonstration of the software, also in 15 to 20 minutes. And then we have about 15 to 20 minutes left for your questions. The title of our session is indeed Geosimulation with Fields and Agents. And I'd like to start with this slide to get us all together on the same page. I think that many of you, at least many of us, work on problems that are somehow related to global change. Here you see listed some of these problems. For example, when we irrigate our croplands, we may cause water shortages, or when we expand cropland to increase food production, we may cause habitat fragmentation. There are also other types of land use changes that may be problematic. For example, deforestation can cause large amount of carbon emissions, or urban expansion can increase the impermeability of soils and thereby increase flood risks. Well, all of these problems that we see here have something in common, and that thing is that there is a certain system, and the state of that system changes over time. And these system state changes in their turn, they have certain impacts that we're interested in. And when we consider these problems as researchers, we typically look at 3 different types of questions. The first question is like, okay, what is the spatial pattern of the system state variable that we're looking at? So this we call a spatial prediction, and you've seen several methods already in this summer school to come, for example, from points to spatial predictions, let's say interpolation methods. But that's typically not what we are working on. We work on other types of questions. For example, how do these patterns come about? So more a question relating to trying to understand the system. And a third question, that is, what will happen to the state of the system and the related impacts if when a certain condition applies. Relating to deforestation, you could say, okay, what would happen if we install a national park here? Is the deforestation then evaded, or is it replaced to another location? And for these 2 types of questions, so the understanding and the one with the condition that we also call scenarios, for that we use geosimulation models. Conceptually, you could see a geosimulation model as depicted here. We implement a transition function f, and that transition function contains a number of rules. We can use our model by giving as input some driver at time step t, and with that we project towards the future the state of the system at time step t, and from that we can use other models to compute the related impacts. Now you may wonder, how this differs from other types of spatiotemporal models, and that I try to outline in this table over here. What we call geo-simulation models are models that are so-called process-based or process-driven models. That means that we implement an existing theory into a computational model. So a certain description of the system that already exists. Thereby, the relations between the components in the system are based on known or assumed cause-effect relations. On the other end of the spectrum, you have data-driven or empirical models. They start with empirical data, and then they fit a model to that. And then you get a model that's based on correlations between drivers and the system state. So that's basically the difference between these two in order to put what we're doing in context of the rest of this summer school. In geosimulation modeling, there are two main modeling paradigms, agent-based modeling and field-based modeling. And this has a certain analogy to vector-based data versus raster-based data. When you model your system as an agent-based model, the system state is consists of a set of discrete objects, the agents. And in field-based modeling, it consists of a continuous or discrete raster. And that means that then your system state variable has a value everywhere. On the other hand, in agent-based modeling, your attribute or your system state variable is linked specifically to the agent, so it doesn't necessarily have a value everywhere. Also, the way we implement processes in agent-based and in field-based model differs considerably. Processes in agent-based modeling are implemented as the behavior of a single agent. And usually one of these behaviors is the way the agent moves through space. And in field-based modeling, we implement it as the behavior of a cell that remains in its location. So the cell can only basically change its state over time. Now, a problem that we can already recognize here is that many of the systems that we find in the real world, they have multiple phenomena, and these phenomena in a system typically do not fit into one of these paradigms, but systems have components where some are intuitively more agent-based and others are intuitively more field-based. An example of a theory or a system that contains both fields and agents is a very old one that's called Daisy World. Daisy World is a theory introduced by James Lovelock and Andrew Watson in the 80s in order to illustrate the Gaia hypothesis. And the Gaia hypothesis tells us that organisms interact with their non-organic surroundings, creating thereby a self-regulating system. So here you see a picture that represents Daisy World. Daisy World has one field, namely the temperature of the Earth's surface, and it has agents, the daisies, and there are two types of agents, black daisies and white daisies. And this theory, it tells us that there's difference between black and white daisies, namely the white daisies have a high albedo. That means that they reflect a lot of sunlight, and thereby they cool down their surroundings. So they influence this temperature field in a negative way. Black daisies, on the other hand, have a low albedo, so they absorb light, and thereby they warm their surroundings. And another property of these daisies is that they can exist and reproduce only in a certain range of temperatures. And that causes the following effect that we see here in the graphs, that when the temperature of the Earth is high, the white daisies thrive because they manage to cool down their surroundings enough to be able to reproduce. And so more white daisies come about, and the white daisies cool down the temperature of the Earth, and then it becomes more suitable for the black daisies. The black daisies increase the temperature of the Earth, and thereby you get this kind of dynamic equilibrium caused by the daisies, and that's the self-regulating effect. So to come back to software, the current software that enables modeling both fields and agents often departs from agent-based modeling. That means that it approaches a field as a set of square objects, the grid cells, And that makes it computationally suboptimal because it means that you have to loop over all the cells in your raster in order to implement a certain method. So that's not ideal. NetLogo is an example of such a modeling environment. Also, often these software have separate sets of functions for fields and agents, so that requires quite a lot of expertise from the modeler to decide exactly how to implement something. So the problem that we see here is that there is at the moment no software with full integration between fields and agents. So what we're introducing here today is the software Compo. And the idea of the software Compo is that a user can build his or her own model with it. For example, the Daisy World model. The user can apply for that Compo, which is a Python library, and that Python library is based on 3 things. First of all, it's based on the LUI data model, and that's important here because the LUI data model considers the world hierarchically. So we will also later see that that you need that hierarchy when you apply Compo functions. Furthermore, it's based on HDF5, which I won't go into detail about. And it's based on the PC raster library. It uses the PC raster library for the control flow of the model. That means in order to implement mainly the temporal aspect of your geosimulation model. So to come back to this hierarchical structure, the LUI data model sees at the highest level of hierarchy a phenomenon. And a phenomenon can be either an agent or a field. That doesn't matter. So here we see an example. Here you could see this as a phenomenon trees. So there are certain trees scattered in our study area. We can also have a field phenomenon, for example, a digital elevation model of the study area. And of course, these two interact with each other. At the second level of hierarchy in the LUI data model, we have property sets. So when we look again at our trees and we study them in a bit more detail, we can notice that trees have stems and they have a canopy. And the process that we want to model is perhaps seed dispersal in the surrounding of the trees. So we can separate these 3 things and regard them as 3 different property sets. So we have a property set stem, a property set surrounding that we will later use for seed dispersal, and a property set canopy. At the lowest hierarchical level then of Compo and of LUI data model, we have properties, and properties, I think that's quite intuitive. So a property is a certain attribute. And for example, the canopy could have a property NDVI. So this hierarchy is also important for the syntax of the functions. So the general syntax of functions in Compo is like we are used to in Python. We have a function here, for example, called a function. It takes an input B, and it generates a certain output that is then assigned to variable A. When we work with our phenomena in Compo, we use that same function, but then as an input, we specify this hierarchy. We have the phenomenon trees, then the property set, canopy, and the property NDVI. And that is the input that we want to provide to our function. And we also assign it to a property in the same phenomenon, in the same property set. So finally, shortly about the PC raster Python modeling framework that we use for the temporal part of the model. So what I showed before, the Compo functions, they are basically sort of map algebra, a set of functions that you can use to define spatial phenomena. So for the temporal part, we use this dynamic modeling framework where we have an initial method and a dynamic method. In the initial method, we put all the functions that set up our system, so that define its initial state, and for example, define the constants that we want to use in the model. And then in the dynamic, we can implement the transition function itself, so the processes that define the dynamics of the system, and also the update, finally, of the system state itself. So with this explanation, I hand over to Oliver, who's going to give now a demonstration of the Compo software, and he will show how we have implemented the Daisy World model as an example. After Oliver's presentation, you can ask questions to both of us. Thanks.
Okay, thank you very much, Judith. I will share my screen. So, yes, I'm going to tell a bit about the research project that we are currently working on, and that's indeed Compo, our modeling framework. As Judith already mentioned, we have a data model, the LUI data model, which is an HDF-based data storage, which is very versatile in being able to store field-based data and point-based data. So basically for fields and for agents. While it's very versatile, it's also rather low level. So Compo is a Python-based modeling framework, which is giving access to the LUI framework. And I will tell a bit about how we first represent the Daisy World model in Compo. And then I will briefly walk through the model implementation itself that we built in this Jupyter notebook. So as you already heard, the Daisy World model, we have basically individual daisies, and we have a temperature field. So that's what we couple in or model in two different phenomena. And we call this phenomena daisies for the daisies, and climate, where we basically add the surrounding. Every phenomenon can have basically a domain, and in a domain, the spatial and the temporal concepts are covered. So for the daisies, basically it means daisies are point agents. They have an X and Y coordinate. And for the climate or the surrounding area, it's a field domain, which is basically a bounding box and defining a two-dimensional raster. Every phenomenon and has several properties. For the daisies, that's what we actually want to model. The albedo, the breed, the age. And every property that shares the same domain is grouped into a property set. So in this case, the albedo, the breed, and the age, all they are coupled to the XI coordinate of a daisy. For the temperature field, or for the spatial domain, we have a temperature field and the albedo. Both are two-dimensional fields, and they are bound to the surface property set. So how does this now look in the Python model script? Basically, we have a model instance that we create. So Daisy World is just a Python object where all the phenomena can be attached to. And this is basically done with the add phenomenon method. And in our example, we have two phenomena, the daisies and the climate. And what this method basically is doing, we create two empty phenomena. So there's just nothing held by them. The type of the agents, if it's a point agent or if it's a field agent, that's defined when you add a property set. A property set, like shown in the graph here, holds basically the domain, the spatial domain, defining the type of the agent and also the number of the agents. And if we have a phenomenon, we can add properties with the add property set method. And actually, we are reading in from input data sets, and these are basically just text files having X and Y coordinates in the case of the daisies, and also defining the number of agents for the field. we have a surface property set, and in the area input file, there's actually a description of the bounding box and the number of rows and columns. In the Daisy World example, we have the special case that we only have one field agent. Basically, we could have several field agents. Think, for example, you have different catchments. Then you would also have different field agents, and each having its own catchment. For the Daisy World, we only have one field agent. If we have now defined the property sets, we can basically just add properties. And here is given an example. So we have this kind of dot notation in Python, giving the triplet of phenomenon, property set, and property. And in this case, we just create a new property age, and all agents which are now in this property set get the initial value of 0. Similar applies to the field agent. We have again our phenomenon property set property, and we initialize it with the value 0.4. And in this case, it means that every raster cell in the field agent gets the value 0.4. If we have now this well, phenomenon and property sets and properties initialized, of course we want to do operations on that. And how does it look like? Well, you did already mentioned. We are looking to some kind of map algebra-like approach that you can operate on the properties. And it basically shouldn't matter that much if it's a point agent or if it's a field agent. So how does it look like in the well, very simple case? All kinds of arithmetic operations that can be just applied to both of them, to both types. So if we want to increase the lifetime of daisies, we just use again the triplet notation, and we increase the property value by 1. So this means all agents, the age will be increased by 1. Regarding the syntax, is the same also for the fields. The temperature field, we just increase it by 1, which means in our case, every raster cell in the temperature property will be increased by 1. So in Compo, we provide all kinds of arithmetic operations or comparison operations. So basically, it's a mapping, so to kind of NumPy operations, so that we can just use them out of the box and then write mathematical equations. We also have the kind of set of operations. If you want to have, for example, for every agent an individual value, we can, for example, use the uniform function. And the uniform function takes also 2 arguments. So basically a lower boundary and an upper boundary, which could be the same for every agent or which could be also different for every agent. But basically with the uniform function, every property in the Daisy agent will get a different value. Using the same function, but now applying it to a field agent, every raster cell value gets a value drawn from a uniform distribution. So the basic idea is that we can just use, like a map algebra, the same operations or same set of functions, either on point agents or on field agents, and they should just work. We also have a bit of, a few operations which can interoperate between phenomena. So basically, if you want to have, for example, as a Daisy, we need to know the temperature value from the field. So this is some kind of special operations between different phenomena. So what we actually try to do is to develop some kind of classification of operations which can be just operate both on fields and agents, between fields and agents. So if you want to know a bit more about that, you can also have a look on the operations and type of operations that we provide on our documentation website of Compo. So, but how does it now look in a Python script? I will briefly go to the notebook. Well, first of all, we just import the Pythonic way. We import the required modules. We use quite a few of them. The PC raster framework, as you already mentioned. In this, we use it for the dynamic modeling, but also under the hood of Compo, we use it also to calculate the field-based operations. Compo is also a collection of more modules. So it's basically using NumPy, GDAL, X-array, and Network X, for example. So we use different functionality from existing Python modules here. We have some kind of utils module, which covers all kinds of methods that we use, especially for this notebook for the visualization of some output. First step that we need to do is basically generating the input files. As already mentioned, the input file defines basically the type of the agent and the number of the agents. And this helper functions generates two files. One file for creating one field agent. In this case, we have, well, now 20 rows, 20 columns, and the corresponding bounding box. And a second input file will be generated where we, in this case, put one agent, so one daisy, basically into one raster cell. As some kind of side note, for reproducible results, we set the random seed fixed, so that always we will get the same output in this example. As an input to the model, we have the luminosity, and we define 4 different scenarios that you can specify as input data to the model. And we have 3 times fixed luminosities, and these are basically the scenarios low, high, and hour. And we have a 4th scenario, the ramp scenario, where actually the luminosity as an input changes over time, and I will show how it looks like a bit later on. So with this kind of well, pre-definition, we can have a look at the Daisy World model itself. And well, it's nothing extremely special if you're a bit used to Python. So we have the standard class we derive from the PC raster framework to provide the dynamic modeling capabilities. And in the PC raster framework, we basically implement 2 methods. That's the initial method, where we define the initial state of a model. And here again, we basically find back what I just introduced, basically from the top until here. We create a model instance, we attach the Daisy World phenomenon, we create the daisies, so we read in the input file that we just generated, and we initialize a property with a particular value. And this is done for more properties. So there's quite some initialization here, and I will skip this because it's more or less more of the same. As a second step in the init method, we create also the second phenomenon, so the temperature field, also or the field agent. And again, it's well, the surface property set, in this case defined with one field agent, and also we attach to that different properties like temperature field and the surface albedo. For the scenario definition, we just choose different starting luminosities, and well, in the RAM scenario, it may change over time. Another thing what we are doing is, well, we define the model run as a real-time date. So we can set particular dates, and we can set time stepping. So for the Louis data model, we actually map real-time data or real-time time steps to the data set, and that's actually done in this section where we just use, for example, a monthly time step. By default, we assume that the properties are static, so that you can just write them once to a data set and they do not change over time. So in this section, what you see here is basically a hint to the Compo framework that we actually would like to have changing values over time of certain properties. And this is, for example, yeah, for the daisies, the lifetime, so the age, and for the climate, it's the temperature field that will change over time. After we did this, we can just write the initial state to the data set, which is just well, the right method. So now we can write the initial state to the Louis data set. What is done in the dynamic section? I will briefly go through this. The dynamic section is executed every time step. So this one holds the process description of what needs to be done every time step. And this is basically calculating the surface temperature of the current time step. We have this interaction between daisies and temperature diffusion. So that's also calculated. We have spreading of the plants based on some kind of temperature window, if it's okay to spread or not. We have the solar activity, and we also increase the lifetime of, or the age of the daisies per time step. And how do the process descriptions look like? Well, you can already see here for the spread plants. It's again like the mathematical description, the map algebra way of implementing the functions or the processes. And here we have a C threshold, which is calculated basically on the field agent. So we have, again, the phenomenon climate, property set surface, and the temperature. So this is kind of calculating the well, suitable temperature for seeding or not. Again, we have the uniform method to create some kind of spreading threshold for the daisies. But basically, it's yeah, writing the process descriptions in a mathematical way. And also the other operations or methods like the diffusion and surface temperature, they're expressed more or less in this way. So I will skip the implementation here right now. So basically, if we calculate every time step, well, yes, we write the time step state to the dataset as well. So with this write command and the information which properties are set to dynamic, they all should be written to the dataset. If you want to run the model, yes, well, that's basically the implementation of the model. If you want to run the model, we can have some kind of different input arguments. Yeah, like the number of time steps, the initial fractions, and albedos of the different daisy breeds. And also we set the scenario, so the luminosity that we want to run in the model. And that's basically where, if you want to run the model yourself, you can play around a bit with the values in here, and then you can run the model. So if you do that, well, then there's no particular output. The model is running every time step something is written to disk. And this, well, in the end, the only result will be some kind of Louis data set that will be written to disk. And this data set we can use to obtain results from. And how does this look like? First of all, we have some kind of plotting utilities. We can have a look at one of the input values, so the scenarios, so the luminosity value in the first scenario that it was running is actually constant. So and this is for all the 800 time steps, we have a fixed luminosity value. So there's nothing very interesting about this input value. But what we would like to see, or what is much more interesting, is to have a look at the spatial temporal pattern. How do the daisies evolve, and how does the temperature evolve over time? This is stored in the data set, so we have some kind of plotting method where we can extract the corresponding data, and then you will generate these kind of plots. So we have our basically our field. We have the black and the white daisies, and we can have a look how they evolve over time. So this is now the way how you can basically investigate some kind of spatial temporal patterns and how the model behaves over time. What we also can do from the existing data set, we can calculate some kind of statistics. So, for example, we would like to know what is the average temperature of the area, and that's what we can actually plot with this kind of method. And we see that after some time we have some kind of development around or somewhere between 20 and 25 degrees. Another thing that might be nice to have a look at is how does the population evolve? So we also extracted from the Louis dataset, and we can see here the population development of the black and the white daisies. That there's some kind of counter development of the numbers, and that we have in the end some kind of dynamic equilibrium over time in this kind of luminosity state. So this is one model output, and for comparison, I briefly would like to show the RAM scenario. So here we have now different input values over time. So then in the beginning we have constant. After 200 time steps, it's increasing up to the about 400 times step 400, and after 500 we have a decrease in luminosity again. So how does this now look like in the animation? Same concept. After the model run, we extract the output data, and we can have a look at the output. And perhaps you already recognize, but this is quite a different pattern. So we have a dominant species in this case. So it's the black daisies. And well, we have time step 200, so we have an increase in luminosity, and suddenly we also have some kind of response in the type of plants, and we see that something extremely is happening in our model. And so corresponding to that, we can also have a look at the average temperature in the model itself. So again, we see the development in the beginning. It's more or less in the fixed luminosity. When the luminosity changes at times to 200, we have quite an abrupt change. And this kind of development, we also see it back. We've also seen it in the visual interpretation. In the beginning, we had some kind of dominant black breed, and afterwards, with increasing luminosity, the right breed has a higher chance for spreading. So this is basically just giving two kind of output examples, and this also introduces how basically the DAISY world model with an interaction between point agents and field agents is implemented in the current version of our Compo framework. And with that, basically, I'm more or less finished with my part. I would like to stress that it's really a research project that we're currently working on. So yeah, our idea is indeed to have some kind of map algebra approach where we can write one model representing point agents or field agents. We have quite some things to do. So not all of the functions are implemented in Compo. For example, like moving agents, that's one thing that we currently want to look at. We have the backend, the LUI is not only a database or a data storage, but LUI is also a framework for modeling. So basically, we want to replace part of the functionality implemented by the LUI framework. And the capability there is by using HPX, we can use distributed computing and such being able more, to provide more computational power to these kind of models. And what we are actually interested in would be, what kind of case studies are you working on? Do you have kind of field agents or a coupled model? And do you think this kind of Compo approach could be interesting for you? So with that, I'm kind of finishing my part, and I think we have quite some time for questions.
That's a good thing.
Good, thank you, Oliver and Judith, for this interesting presentations. We have a couple of questions on the Mattermost going on. Let me see. From the Zoom chat, there was one that related to the DAISY model, I think. Beside temperature, why not use water in the model?
Yeah, thanks. So an important thing to stress here again is that when you build a geosimulation model, it's usually based on an existing theory. And that's also what we demonstrated here. So DAISY world is a theory that someone has came up with in the 80s. And what we did here in our demonstration is implement that theory or that model into a computational model that you can run. So it wasn't our decision to use only temperature and not water. That's simply defined by those scholars that came up with this theory or model. Mm-hmm. That doesn't mean that it's impossible to implement water. So if you have a system in mind that contains temperature fields and also water, that's definitely possible. It's possible to implement that.
Okay. Another question that came up there, how can I access the Compo model? And I already submitted the website of the installation to the installation of the software, which I found. But the sort of the DAISY model that you demonstrated, this Jupyter notebook, is that also available there as one of the demo?
Yeah, the repository that we have, we share the Jupyter notebook.
Okay.
So you can run it yourself. Actually, we could also add a standalone model, but the repository, there's also the Python environment that you need to run everything. So there's some kind of install instruction, how to run the Miniconda environment to create it and to run the Jupyter notebook. So everything what you need to run this Jupyter notebook is involved in the repository that we shared in the Judith's Mattermost channel.
Okay.
But it's a good thing to clarify indeed that Compo is a software package. So it's a Python library. Compo in itself is not a model. You can use Compo to implement your own model, for example, DAISY world. So the Compo model is not a thing.
It's a Python module that is used in this Jupyter notebook.
Exactly.
Yes. Yeah. So basically, Compo just provides all kinds of functionality, like the different operations. But yeah, how you combine these operations to your model, that's really left to the modeler. So if you want to implement your groundwater model with different fields representing different catchments, yeah, then you need to implement the processes for every catchment. But yeah, that's left to the modeler.
And there was a question that I don't actually completely understand. Is there a limit for this property set in ABM? I don't know exactly which property is referred to here. This was already sort of posted half an hour ago.
Well, if it's really referring to the property values that are attached to a property set, yeah, I would, well, basically no. But of course, yeah, at some point you're limited to the available memory and amount of agents and data that you want to represent. But basically, it should be fine to attach, well, as long as properties share the same spatial and temporal domain, they should be able to be attached to one property set. And there's no particular limit. There's no reason for a particular limit.
Limit to the number of properties, you mean then?
Yes, yeah.
Okay. Next question is, what would be the major differences when modeling moving agents?
Basically, what I've shown now, or what we implemented now is operations on property values. So the plus or the uniform, they operate on the properties. If you implement the move operation, you basically would operate on the property set, or more specifically on the domain of an phenomenon. So for the point agents, you would change the coordinate pair for each agent. But also for fields, you could also think of the move operation. You could also move fields in space, which then for fields would then basically that you move the bounding box to a different origin. For catchments, obviously not feasible. But if you have, yeah, I can't think of a very good example.
You could think of a rainfall field, right? Which you could, in principle, it could rain here, it could rain there.
Yes, yeah. So then you would have changing values in the property values, and also changes in the domain values. So you have the intensity would then the changes in the intensity would be covered in the property values, and the changes in space would then be held in the property set.
Okay, good.
So we have, yeah, that's the idea of different classifications and where actually operations are working on.
Yeah. And another question, it's probably easy to answer. Can the model work with 3 kinds of daisies? I guess that is the same, like 3 kinds of daisies. You had no black and white daisies. Could we have black, white, and red daisies? For some reason?
Yeah, basically, yes.
Yeah, it is.
Sure. So again, this is just an existing theory that we implemented, and that theory tells us that there are black and white daisies, but you could use your own imagination to add more, and the modeling software is not limiting for that.
So the next question is, can the model investigate the behavior of 2 different crop types, for example, in the agroforestry concept? Has that been done before?
Do you want me to answer, Oliver?
Yeah, if you have a very brief answer to that, yeah, well.
So the Compo software is still in development, so not many models have been implemented so far. Maybe later Oliver can mention the examples that they are working on. But the PC raster Python framework that we also used in our implementation has been used more often, and also for crop models. For example, I myself worked a lot with land use change models, where I implemented different land use types, for example, 2 types of crops, and that there was a competition for land, that one crop expands over the other. And in response, the other crop had to appear somewhere else in order to still make sure that the demand for that particular food type is met. So those types of models are indeed also implemented, could be implemented in the future in Compo, and have, as of now, been implemented also in the PC raster Python framework. But that framework, the difference is that it only works with rasters and not with agents.
Okay. Yeah.
What we are currently working on is rather related to the health topic. So basically, we have air pollution fields and people that are in this air pollution field. So that's one of the application cases where we use for the time being basically the LUI storage.
Mm-hmm.
And an other example that we developed is some propensity for healthy food. So we have a city where you have food outlets and inhabitants, and there's some kind of interaction between how healthy the food supply is. The more healthy also people tend to eat. So this is a bit of kind of models that we're currently working on and that have been implemented. But yeah, it's a research project, so we are progressing with kind of application cases, and we're adding more functionality that we need for that. So
yeah. Right. Could I exchange data in both directions with a standard GIS, maybe for each step, for each time step? Yes.
It is not really implemented. What we have done for one of our cases is that we basically exported the agents to geo packages.
Mm-hmm.
So the agent locations and the attributes, we put it into an attribute table and that into a geo package.
Mm-hmm.
Then it evolves, or basically the steps are still, you write it to a LUI dataset, and afterwards you can extract it and convert it to another format. Also for the input side, we didn't implement too much, but you also could think of the same thing, that you instead of generating this text file for the time being, you could also read a points data set that defines then actually the agents, at least the locations of the agents. So the functionality is not there, but basically that would be some kind of pre and post processing input around that. But yeah, with more kind of GDAL support and usage, we can come quite far in exchanging.
Okay.
But also the functionality that we now have. So we have points and two-dimensional agents. The LUI data model itself, it would be capable of storing more kinds of domains, like lines or other kinds of polygons. So if you're free to store those ones as a domain information as well. But yeah, that's what is not yet implemented in Compo. So we have this kind of main application cases of point agents and the PC raster background. So the field agents.
Mm-hmm. Yeah, but you work with PC raster maps, grid maps, rasters, right?
Yes and no.
Oh,
yes.
Okay. Okay.
For some of the operations, we use just NumPy operations. So also for the 2D plus, for example, we also fall back to the NumPy plus. But for the spread or the slope or some kind of for example, kinematic wave, we would then map that to the PC raster operations at the moment.
Okay.
So what's then happening underwater is that for every field agent, a PC raster operation is executed and then returns the new value to the field agent.
Mm-hmm. Next question, do you also derive some measure of uncertainty of simulations per pixel, or is the system semi-chaotic?
That can definitely be done. So what we showed now, for that we used the dynamic modeling framework in PC Raster, but PC Raster also has a stochastic modeling framework, and that doesn't only have an initial and a dynamic, but there you run basically the dynamic several times. So you create a Monte Carlo approach to the model. And then there's also a post loop function that computes summary statistics over your Monte Carlo approach. So then you can compute the effect of the uncertainty in your model on the system state variable that you're interested in.
Kind of error propagation now.
For error propagation modeling, yes.
Okay.
I remember contributing to that. There is a very
Been a while.
There's a very old paper. Will this model can this model be used in R? Short answer.
No.
With a lot of,
Short enough.
a lot of effort, you could re-implement it. Yeah.
Well, at least there are several implementations of the Daisy World model.
Of course, yeah.
But well, I'm not aware of. Well, I'm not a very experienced R user, so yeah. Well, at least this kind of this model implementation, not no.
But with the reticulate, you could load a Python library, and then you just run it from R.
That is fake.
Yeah, but it's possible.
Okay.
You could build on top of.
But you're right.
Could build on top of, yeah.
You're right.
Not sure why you would want to do that, but in theory you could.
Python code in R. That's right. Yeah, and vice versa. Yeah. Right, and then there's a comment from Tom Hengel that maybe the speakers could also point to this paper where the link is in the Mattermost, if that is sort of a relevant reading background for the ideas behind this.
It's called a physical data model.
Yeah, so there are basically 3 scientific papers related to what we presented, and they are also linked in the repo of the GitHub repository.
Ah, okay. So there is more extensive references on the GitHub page of this module. Yeah. Okay, good. Right. So are there any remaining spontaneous questions, maybe from the panel?
I see a question in the chat from Gilberto.
Go ahead, Gilberto, you can speak, right? Let me see.
Yes, I can speak. It's to ask you, Judith, and first of all, congratulations, a very nice work. The Daisy World is really a nice model. The question is, of course, there is substantial work being done in other modeling frameworks. So that's NetLogo, Repass, Mason, Teremi. So could you just briefly compare your approach and say, like, rapidly pros and cons? I mean, not any detailed answer.
So actually, this is something we are planning to do. So first, we need to implement a couple more functions into the Compo software. But what we plan to do is to write a paper where we compare Compo with at least NetLogo and perhaps Terame. So there's one thing that I already mentioned in the presentation, that in NetLogo, everything is basically an object, and an individual grid cell in the raster is seen as an object. So when you want to implement a function on a raster in NetLogo, you loop over all individual grid cells, which is, of course, computationally quite expensive to do. Oliver, do you have some additional things?
Then there's one thing regarding the data storage, for example. If you have a property like the age, all age values of all agents are stored in one array. So, and not for every object has an age value. So if you want to increase the age value, you just have to increase the value of an entire array without indeed looping over every object. So this should be some kind of data-oriented storage. rather than the object-oriented storage of an agent. So every property value has its own kind of access and storage pattern, and if you operate on that, that should be basically it should be beneficial regarding the performance.
Thank you.
Okay, thanks. With an eye on the clock, Tom, am I right?
Yes, we are just on time. It's time to finish this block.
Good. Then let me
yes.
thank Judith and Oliver very much for your contribution, and also Aya for his for the first block. And then we have a break, and we see you back after the break.